Solved problems. First problem, prove for all x there exists y such that x equals y. This is, in other words, saying everyone is someone. Seems pretty obvious, but how to prove it from the axioms of identity? So we want to show that whenever x is given, there is some y that is identical with x. Of course, we choose x itself as y. Here is the natural deduction. We aim at for all x there exists y, x equals y. This is a universal statement. Starts with a universal quantifier. Okay, we try universal quantifier introduction, and of course this is only possible if x is not free in our assumptions, but we don't have any assumptions, so that's probably okay. So how to derive there exists y such that x equals y? We can get it from x equals x, because if we take the formula x equals y and substitute x into y, we get x equals x. And x equals x we can get from the identity axiom for all x, x equals x by universal quantifier elimination rule. And now we can observe that the final application of the universal quantifier introduction was legal. We didn't use any assumptions with x free. X is not free in the identity axiom for all x, x equals x. And we are done. Second problem. Prove for all x0 left parenthesis px0 implies for all x1 left parenthesis negation px1 implies negation x0 equals x1 right parenthesis twice. In a sense, this says that whoever sings is not identical to anyone who doesn't. We want to show that whenever a singing A is given and also a non-singing B, then A is not equal to B. We use the fact that identity preserves all properties, so A equals B leads to a contradiction. Here is the deduction. We want to arrive at this universally quantified formula. So we want to use at the end a universal quantifier introduction rule. And we have to make sure that x0 is not free in the assumptions. Well, we don't have any assumptions. Now this is an implication. So we use implication introduction rule. We make the assumption p0 x0 and try to derive for all x1. Negation p0 x1 implies negation x0 equals x1. This is again a universal formula, so we try to use the universal quantifier introduction rule. So we have to derive an implication, and again we put the hypothesis as a temporary assumption and try to derive the conclusion. Negation x0 equals x1. This is of the form of a negation. So we make the assumption x0 equals x1 and try to derive a contradiction. If we now look at our temporary assumptions, p0 x0, not p0 x1, but also x0 equals x1. These temporary assumptions clearly contradict the identity axioms. So, with the help of the identity axioms, we can get a contradiction. From the identity axiom, we get that if x0 is equal to x1 and p0 x0, then p0 x1. And from x0 equals x1 and p0 x0, we get x0 equals x1 and p0 x0, and finally p0 x1. Now we have a contradiction, and from the contradiction we can use negation introduction, and we are done. Next problem. We want to prove exists x0 for all x1, x0 equals x1 implies for all x2, for all x3, x2 equals x3. Intuitively this says that if there is just one element in the universe, then any two elements are equal. Let us think about this. We assume that there is some A such that every element is equal to A. Then we take two elements x2 and x3. So we know that A equals x2 and that A equals x3. By the symmetry axiom, we get x2 implies A and A equals x3. And then by the transitivity axiom, we get x2 equals x3 as desired. Let us then write the deduction. Our claim is an implication, so we take the hypothesis exists x0 for all x1, x0 equals x1 as a temporary assumption, and try to derive the conclusion for all x2 for all x3, x2 equals x3. This is a universal statement, so we try to use universal quantifier introduction rule and derive x2 equals x3. At the same time, we observe that our temporary assumption exists x0 for all x1, x0 equals x1 is an existential statement. So in order to use it, we probably have to use the existential quantifier elimination rule, which means that we take the temporary assumption for all x1, x0 equals x1, and now we try to derive x2 equals x3. We use the fact which follows from transitivity of identity that if x2 is equal to x0 and x0 is equal to x3, then x2 is equal to x3, the transitivity of identity. Now, from the temporary assumption for all x1, x0 equals x1, we get x0 equals x2 by simply substituting x2 to x1. We also get x0 equals x3. This identity x0 equals x2 we have to turn around by means of the symmetry axiom in order to get x2 equals x0. Now we put these two identities together and use the implication elimination rule, and the implication which expresses the transitivity we get from the transitivity axiom by three applications of universal quantifier elimination, and we are done. So the thinking here follows these arrows. We want an implication, so we make a temporary assumption. We take the hypothesis as a temporary assumption and try to derive the conclusion. To use the existential quantifier elimination rule, we make the temporary assumption for all x1, x0 equals x1. From there we get x0 equals x2, and from there using symmetry, x2 equals x0, and then using another identity we get x2 equals x0 and x0 equals x3. And when we apply this to the transitivity axiom, we get x2 equals x3, which is what we needed, and then we just use universal quantifier introduction rule, and we are done. Next problem. Prove from the axioms of order that if x is less than y, then not y less than x. So let's think about this. Suppose x is less than y. Why is it not true that y is less than x? Well, if y was less than x, then by transitivity x would be less than x. But by anti-reflexivity x less than x is false. So y less than x leads to a contradiction, and we may conclude that y less than x is false. Here is the derivation. We want to derive an implication. So we take the hypothesis as a temporary assumption and try to derive the conclusion. The conclusion is a negation, so we try to use negation introduction rule, and therefore we make a temporary assumption and try to derive a contradiction. So now we have two temporary assumptions and they should lead to a contradiction. When we put them together by conjunction and then apply this to the transitivity axiom, we get x less than x. On the other hand, there is an axiom which says that for all x not x less than x. So we have a contradiction and we are done. The thinking here was that we want an implication, so we make a temporary assumption and try to derive the conclusion. Conclusion is a negation, Again, we make a temporary assumption and try to derive a contradiction. So from here we go to the conjunction, and then we use identity axioms, and we get the contradiction, and we are done.